This discussion will focus on some fundamental elements of hemodynamic calculations in echocardiography. It is meant as a starting point, but is by no means comprehensive. The learner is encouraged to explore the additional information provided for further study. In order to calculate cardiac output, several concepts must be understood and employed. The stroke volume is defined as the total amount of blood leaving the ventricle during systole. This includes both antegrade and retrograde flow. Cardiac output is defined as the amount of blood circulating through the body over time. In order to calculate cardiac output, stroke volume is therefore multiplied by heart rate. The stroke volume can often be assumed to be the volume of blood leaving the left ventricular outflow tract. The outflow tract area can be assumed to be a cylinder, the area of which is the cross-sectional area times the height. The height of the cylinder is defined by the velocity time integral, a measured value obtained via pulse wave interrogation of the LVOT in the deep transgastric or transgastric long axis view. The resulting envelope is traced in order to find the area under the curve, which is called a velocity time integral, or VTI. This number represents the stroke distance that the sample of blood travels and is measured in centimeters. The cross-sectional area of the left ventricular outflow tract is assumed to be circular and thus calculated using the fundamental formula pi times the radius squared. This can also be reconfigured to use the diameter, since 0.785 times the diameter squared is equal to pi times the radius squared. The diameter of the LVOT is directly measured in the mid-esophageal long axis view of the aortic valve at an angle of 120 degrees. Values for the cross-sectional area are measured in square centimeters. Multiplying the cross-sectional area in square centimeters by the velocity time integral measured in centimeters results in a stroke volume value in cubic centimeters, or milliliters. Bernoulli's equation defines the relationship between pressure and velocity in a closed fluid-filled system. Pressure varies as the difference in the square of velocities in the system varies, and also depends on the flow profile and viscosity of blood. We will later see how this relationship can be simplified in practice for most situations. It is important to understand the difference between a peak and mean gradient. The peak gradient, or peak instantaneous gradient, represents the highest instantaneous gradient obtained as blood flows through a narrowed orifice. On the other hand, a mean gradient is calculated over time as the average of multiple instantaneous gradients. Given that the gradient changes throughout the ejection phase, the mean gradient will be a lower number than the peak gradient. Bernoulli's equation may be modified to express a simple relationship between pressure and velocity of blood flow, which is valid in most situations. The peak pressure gradient is equivalent to 4 times the peak velocity squared. Recall from the last slide that a mean gradient can only be measured by tracing the velocity time integral to utilize the velocities obtained throughout the ejection cycle. The continuity equation serves to express the relationship between flow over time in a closed system. Assuming there are no leaks in a fluid system, the volume traveling through one part of the system must be equal to that going through an adjacent part of the system at all times. Thus, if one area is narrowed, the velocity at which the fluid travels must be higher to balance the equation and preserve continuous flow. The best example of this at work is the differing sizes of the LVOT and the aortic valve. Therefore, the cross-sectional area of the LVOT times the velocity time integral of the LVOT must equal the cross-sectional area of the aortic valve times the VTI of the aortic valve. Since the cross-sectional area of the valve is smaller than the LVOT, blood must travel at a higher velocity over time to keep the flow equal. Thus, the VTI of the aortic valve is always higher than that of the LVOT. This relationship is useful to exploit when establishing aortic valve area. The cross-sectional area of the LVOT can be easily calculated, with pi times the radius of the LVOT squared, and the VTI for both the LVOT and the aortic valve can be measured in the deep transgastric view, since the pulse wave at the LVOT gives the LVOT envelope, and continuous wave Doppler through the valve gives the aortic valve envelope, both of which can be traced to provide the respective VTI values. The only remaining unknown is the area of the aortic valve, which can be found by dividing both sides of the equation by the aortic valve VTI. The first step in the calculation of the cardiac output is careful measurement of the left ventricular outflow tract diameter. Because this value is squared in the calculation, even small errors can be magnified. It is recommended to take multiple measurements at a reduced depth or while applying the zoom function to closely observe the borders of the LVOT. The LVOT should be measured while the valve is open and the walls appear parallel to each other. The measurement should be within 1 centimeter of the valve. The velocity time integral for the left ventricular outflow tract is obtained by advancing the probe into the stomach past the mid-papillary view, then anti-flexing the probe until the apex of the heart is seen at the top of the screen, and the LVOT, aortic valve, and ascending aorta are seen at the bottom of the screen. The pulse wave Doppler beam can then be applied, positioning the cursor in the LVOT within 1 centimeter of the valve, as close as possible to the same place the LVOT diameter was measured in the mid-esophagus. Once the Doppler envelope is obtained through the LVOT, a velocity time integral can be traced. A heart rate can also be measured. Some machines will record this automatically, while others require marking from R wave to R wave of the ECG to measure the heart rate. In summary, careful measurement of the LVOT diameter in the mid-esophageal aortic valve long axis view is followed by obtaining a pulse wave Doppler for VTI of the LVOT in the deep transgastric view or transgastric long axis view. What follows are case examples to test your knowledge of these concepts. Scenario 1. Using the following data, please calculate in sequence the peak gradient, stroke volume, cardiac output, and aortic valve area. Peak gradient is calculated using the modified Bernoulli equation, 4 times the peak velocity squared. In this case, the peak velocity is 4.4, so the peak gradient is 77.4 millimeters of mercury. We will now move on to calculate stroke volume, cardiac output, and aortic valve area. Stroke volume equals the cross-sectional area of the LVOT times the velocity time integral of the LVOT. Since the velocity time integral of the LVOT is measured as 12, we need only to solve for the cross-sectional area of the LVOT, which is pi times the radius squared, or pi times half the diameter squared. In this case, the radius of the LVOT is 1.075 centimeters. Thus, the stroke volume is 43.5 milliliters. Since cardiac output equals stroke volume times heart rate, and the heart rate is 64, we calculate a cardiac output of 2.8 liters per minute. Our final calculation of the aortic valve area is obtained by rearranging the continuity equation to solve for aortic valve area. The numerator is the stroke volume, and since we already solved for the stroke volume, we simply divide this by the measured velocity time integral through the aortic valve to yield a resulting area of 1.9 square centimeters. Scenario 2. Please read the following scenario and be prepared to calculate the stroke volume, cardiac output, and aortic valve area using peak velocity. Stroke volume calculations are accomplished using the continuity equation as discussed earlier. We have the VTI of the LVOT as 20 centimeters, so we just need to calculate the cross-sectional area of the LVOT to multiply with the VTI as measured. The cross-sectional area of the LVOT is pi times the radius squared of the LVOT, which is half the diameter, or 1 centimeter. Thus, the cross-sectional area of the LVOT is 3.14 and the stroke volume is 3.14 times the VTI of the LVOT. The resultant volume is 62.8 cubic centimeters, or 62.8 milliliters. Once we have calculated the stroke volume, cardiac output can be calculated simply by multiplying the stroke volume by the heart rate, which was given as 80 beats per minute. The resulting cardiac output is 5,024 cc's per minute, or over 5 liters per minute. Calculating the aortic valve area requires us to rearrange the continuity equation and divide both sides by the velocity time integral through the aortic valve. Since we have the velocity time integrals for the LVOT and aortic valve, and solved for the cross-sectional area of the LVOT using pi times the radius squared earlier, we can plug these numbers in and get an area of 0.96 square centimeters. In conclusion, application of the basic principles of hemodynamics can allow us to solve for a variety of variables, from stroke volume to cardiac output and valve areas.